poster blitz, where we will have all of our poster presenters. If you're not already in this space, I encourage you to come down, and Tatiana will help you get in order, and we'll hear about all the wonderful posters. Thank you.
So, while they finish to set up, I'll introduce briefly the session. So this is the Flash poster session. It's the final session of a very long day. It's our final hurdle before dinner, okay? So the way this is going to work is that the poster presenters will come on stage, and they will have 40 seconds to convince you that you should come to the poster session tomorrow morning, okay? And then during the conference, we will vote for the best posters, and I think there will be prizes at the end, yeah. Right? Okay, very good. So I think my main job tonight is actually to make sure that everybody sticks to time, okay? So there is a timer on the slide. When the timer goes off, I will have to kick you out, okay? So that's a good experience, because that's exactly how an ERC interview works. Okay, so I think it's excellent practice. Right, so Tatiana, are we ready to start? Okay, so I think we should just get going. So let's see if this works. Yep. So the first presenter is Sarah, talking about shallow water simulations on complex ocean domains. So you can see the timer is that thing that is ticking. I'll reset it now, and off you go.
Hi, I'm Sarah, and I'm working on ocean simulations. So first, we need a triangulation of our domain. And what we did is we developed a block-structured grid generator. Actually, there's no timer, but that's better for me. And now we improved that. So we have a grid that overlaps the whole ocean domain. And later, we mask some elements that lay on land. And therefore, we can improve the performance and be able to represent more difficult ocean domains. So come to my poster and learn more about this and about improved performance.
Beautifully done. Let's move on. The second presenter is Maximilian, who is going to talk about robust decision-making under risk and ambiguity. So again, I'll reset the clock, and off you go.
Yes, hello. So my work is about dynamic decision-making under uncertainty with this joint work with my co-author Philipp Eisenhower. And we look to dynamic decision-making and look at robust Markov decision processes, which is a way to include parametric uncertainty in your dynamic decision-making. And we try, or we do, merge this literature with statistical decision theory, which is a literature in economics which tries to inform and give guidance on how to take decisions under uncertainty. And we merge these two literatures and can develop a framework which gives us an optimal level of parametric uncertainty you should consider.
Thank you. So next is Alexandros, talking about PILSPAC, fast parallel algorithms, data structures, and software for sparse matrix sketching. So off you go.
So hello, and count sketch is a very popular random projection method for dimensionality reduction, and it's very popular because it's very sparse and very fast, and you can apply it in sparsity time and design cool algorithms. The question is, how do you do it in parallel, and how do you implement it in your computer efficiently? So, sparse computations have a lot of challenges with them, and this is what we did. We just designed parallel algorithms that are efficient, and hopefully you can use our Python package for your data science project. So, thank you.
Okay, thank you. Okay, let's crack on. The next speaker is Teresa, who is talking about scaling plasma simulations while conserving mass. Okay.
Thanks. So you should come see my poster because you want to have the instabilities without the instabilities, right? So There's the instabilities you're interested in, plasma physics instabilities, for instance. There's the bad instabilities. You don't want them. It's numerical instabilities. And our method provides that now, while also providing scaling and accuracy and all the nice things you want to have here at PASC. So please come and discuss.
Right, Paul? Yeah.
Hi, my name is Paul.
Let me read the title.
You want to read it,
I'll
or
let you go.
shall I explain it?
So, circular harmonic oscillator basis for image compression. Off you go.
Yeah, my name's Paul. I'm from Jülich, and Jülich operates a supercomputer, but on the same campus there are other experiments, for example, electron microscopes. And the guys from the electron microscope, they produce so much data in 1 second that they can't really process it. And they want to process it for one reason. They're sitting in front of this microscope, and they don't know which direction to turn a knob. And that's why we need live processing. That's why we have to boil down the processing pipeline latency to below a second, so they can actually see what they are doing. Come to see my poster for the compression methods that we're actually used to get this processing pipeline faster.
Thank you. Frederick, yeah, so enabling ab initio molecular dynamics at the exascale.
Hello, I'm Augustin, and I'm a developer for CP2K, which is a quantum chemistry and solid-state physics code. And here, on this poster, I will talk about the latest development that we made into the code as we go slowly towards exascale ab initio molecular dynamics. So there's an aspect of quantum chemistry and method development as we go to our higher and higher accuracies, and at the same time we need to care about performance, scaling, GPU accelerations, and all that good stuff. So, well, come and say hi if you have any interest in the subject. That would be nice.
Luis, welcome to a new world. Well, go on.
Hi for all. My name is Luis. I'm a PhD student. And I think everybody knows that we have a long participation of women in STEAM areas. So together with a group of research between Brazil and Portugal, we developed a motivational approach that called Heroines Learning Journey. Heroines Learning Journey is based on heroic journeys, and we have 12 stages to overcome these challenges. If you want to know more about this, please come and enjoy together tomorrow. Okay, thank you.
Thank you very much. Okay. Roman, so data-driven analysis of the elder problem using big data. Off you go.
Hello everyone, my name is Roman. My poster is about big data analysis of large ensembles of numerical solutions for partial differential equations. In this case, this is an elder problem. Using big data tools and machine learning, we have analyzed complexity and predictability of those large ensembles and obtained some quite interesting results. Thank you very much.
Thank you very much. Okay, Eric, I don't know where to start reading the title, so maybe you go on.
So you start.
Yeah, no, just go on.
Okay. So it's a long title, but short. Very interesting work. So can I start?
Yeah.
Okay. My name is Eric Frage, a professor at Rutgers University and a chief scientist at Toga Network, a Huawei company. Very nice combination, China and USA. And we are now presenting a very interesting research on weather research forecasting model known as WRF, for which is the most popular model in the last 20 years. And actually, the application of WRF are moving from computing to input-output. In this work, we demonstrate the impact of the new library.
Running out of time. Eric, just go on.
Okay. The new library IDEOs, which impact massively the speed up and also the in situ processing of the model. So you are welcome to come and ask more questions. Thank you.
Thank you. That way. Okay, Sriram Krishnan, Alpine, Plasma Physics Particle in Cell Mini Apps. Go ahead.
Hi, everyone. The goal of the Alpine project is to create a set of performance portable mini apps for plasma physics application using the so-called particle in cell schemes, which are one of the most used numerical methods for these type of simulations targeting exascale architectures. The mini apps are basically lightweight codes which can be used to implement new algorithms, optimize HPC implementations before moving on to production codes. We tested our mini apps on several of the pre-exascale architectures such as Pistane, Cori, Perlmutter, and Summit, and obtained good performance and performance portability and scaling. If you are interested, please do come to our poster. Thank you.
Perfect timing. Thank you. Saurabh, real-time large deformation simulations.
Hi everyone. So in this work, we propose a Bayesian convolutional neural network surrogate model to accurately predict the nonlinear deformations of soft bodies along with the uncertainties. So we basically provide means for you to know that if you should be trusting your neural network model in this particular task or not. So please do come and visit. I look forward to interactions and questions. Thanks.
Thank you very much. Okay, Guillaume, building a physics-constrained, fast and stable machine learning-based radiation emulator.
Yes, thank you. So I'm Guillaume Bertoli. I work with the ICON climate model. This is no longer my poster because research is research. We have new results, new focus. But the idea remains the same. We use machine learning method to predict atmospheric radiation. The goal is to speed up the computation of the radiation. So if you want to know which method we use, please come see me in front of the Sydney room. Thank you.
Thank you. Nicola, high five. No?
Omar, but it's okay. Hi, everyone. Do you
Omar,
deal
yes.
with lots of, that's fine. Do you deal with lots of data? Do you work on modern C++ codes? And do you wish you had an API for HDF5 that actually works with this modern C++? If so, you should come and see Nico and me tomorrow to learn about High5, a header-only C++ library for HDF5.
Thank you. Okay, Ayesha is going to talk about Discostic.
Yes, okay. So this poster is about a simulator that simulates the large-scale applications on recent and future supercomputers. Well, in comparison with the other existing simulators, beyond the communication aspects, we are much more concentrated on below the node level. So we use the analytical first principle performance model for the in-depth architecture explorations, including bottlenecks. Well, here, the DSL codes serve as a blueprint for your application, and you don't need to execute your application. Well, to learn further about this simulator, I invite you to this poster. Thank you.
Thank you very much. Okay. Guillaume is going to talk about physics-inspired representation for atomistic machine learning.
Hello, everyone. So in our lab, we're trying to work with applying machine learning techniques to atomistic systems. And there are a lot of fundamental physical symmetries that exist in these systems. And what we try to do is, instead of representing all of this symmetry in our model and trying to learn this symmetry, we try to incorporate these symmetries from the start in our representations. And then we have a bunch of tricks to improve the complexity and the body order of these representations and then use them. And finally, if you're interested into that, I can also talk about how to implement these in an efficient manner on HPC systems. If you're interested, see you tomorrow.
Thank you very much. Okay, Andrei, GPU support in Gromax.
Hello, everyone. So SYCL is a modern C++-based vendor-neutral framework for programming different hardware accelerators such as GPUs. And in my poster, I present the results of porting a large, well-optimized molecular dynamics engine Gromax to SYCL. I show the results from both software engineering and performance sides to see whether SYCL actually delivers on its promise of allowing writing a performance portable code targeting a wide range of hardware. So come to my poster, and thank you.
Thank you. Michel, DFTK, a Julia toolkit, yeah?
Hi everyone, indeed, my name is Michael, nice to meet you. So I'm going to talk about the Density Functional Toolkit, a Julia-based tool for electronic structure simulations. And unlike many electronic structure codes which are out there, our idea is not really to put out yet another code, but much rather to put out a code which aims at combining between different disciplines and really brings this interdisciplinary bridge in this field. So in particular, it's useful for computer scientists, for mathematicians, and I will present some examples of our recent work to make the code algorithmically differentiable and also to bring forward novel algorithms from the mathematical field over to the simulation domain. So if you're interested in that, I look forward to discussing with you at my poster. Thank you.
Thank you. Next one, yeah. Okay. Very good. So, Jose Roberto is going to talk about Vertex Identification.
Yeah, so hello everyone, I'm Roberto, and I'm going to talk about vortices. So as you probably know, vortices are one of the fundamental features of turbulent fluid dynamics, but they can be it can be very challenging to identify them accurately, for example, in numerical simulations. And that's why we proposed a new algorithm to automatically identify vortices based on the velocity field of the flow of interest. And yeah, for more details, the poster is at 23, and I hope to see you there tomorrow. Thank you very much.
Thank you. Hendrik, a fair digital object-based data lake architecture.
Hi. Data lakes aim to integrate heterogeneous data from diverse data sources into a single, unified research data management system. The general approach to store data in their original format and hereby retaining their value guarantees that the data is preserved over a long period of time. If you want to know why this is also a very good symbiosis with an HPC system, come visit me.
Thanks. Patrick is going to talk about Utopia. Go on.
Thank you. Hello, everyone. So if you're interested in knowing how we simulate fractures, from flow inside fractures to fractures propagation using the phase field method, we have some interesting ideas. Typically, phase field fractures are very hard to simulate because the problem is ill-conditioned, is highly non-convex. And in the literature, you find typically 10 or 20 fractures being solved. And what we actually present here is about 1,000 fractures being solved. And yeah, if you want to know how to do that with open source tools, please visit me and have a nice evening.
Okay, thank you. Is that you?
That's mine.
Okay,
Yeah.
I didn't skip one, right?
No,
that is yours.
correct.
Okay, this is increasingly feeling like presenting the Eurovision Song Contest. So, our next speaker is Matthias, who is going to talk about Docker containers.
Yeah, I will not sing, I will talk.
Excellent.
Yeah, my name is Matthias from the German Weather Service, and in the Symphony project where I work, we want to combine different weather forecast models which by now operate on separate IT infrastructure levels. On my poster, I explain how we build up, how we maintain, and how we execute Docker containers to apply all of these models on one single architecture. Thank you.
Thank you. Okay, Samuel, distributed training of deep neural networks.
Hello, my name's Samuel. So I will be presenting our work on distributed training of deep neural networks based on multi-level methods and domain decomposition methods. So our multi-level methods have gained convergence speed without losing accuracy, and our domain decomposition methods have the advantage of inherent parallelism, and we exploit the global convergence properties of cross-region methods and the near linear, or rather typically linear optimality of multigrid methods. Thank you.
Okay, thank you. Lucas, benchmarking memory-bound computational physics.
Imagine that you are sitting in the front of your computer, you want to submit a job, but then you don't have enough resources, or your queue is, you have to wait for your time. So what do you usually do? Either you wait, you have time, or you simplify your problem, you simplify your simulations. At CERN, what we tried to achieve is the other way around. We tried to expose cloud resources to actually allow researchers to submit jobs without those constraints. So they had theoretically unlimited number of cores, and they could seamlessly submit jobs either to on-premise system or on-cloud system without any interactions. So we demonstrated feasibility of this approach for 3 use cases and 2 CFD and also energy physics codes. Happy to discuss more if you are interested to find out how we did it.
Okay. Thank you.
Hi, so I'm Till. Our poster presents GT4Py. It's a high-performance library in Python for weather and climate applications. So domain scientists can express their stencil computations, for example, horizontal or vertical solvers, in a high-level DSL in Python, and that is then subsequently transformed into high-performance implementation. So happy to see you tomorrow. Thanks.
Thank you. There we go. Oscar, yeah, got the right person, very good. Methodology for estimating effective dissipation.
Yes. This poster from the Istituto Ricerche Solari Locarno presents a method to compute reliable values for the inherent numerical effective viscosity and electric resistivity. And this is done in a post-processing step. So we apply that to characterize dynamo action in the solar and stellar atmosphere. So if you ever wondered what the diffusion coefficients in your simulation code is, then have a look at this poster. Thank you.
Felix is going to talk about performance analysis of nonlinear optimization problems.
Hi, I'm Felix. In our work, we investigate methods to accelerate the solution of nonlinear optimization problems from radiation therapy using distributed computing. The basic idea is to spread the computation of the objective function over different processors while keeping the optimization solver itself on a separate rank. So if you're interested in optimization, radiation therapy, or distributed computing, please come by and say hi at our poster tomorrow.
Thank you. Andreas, topology-aware collective communication.
Hello, everybody. So the poster is about collective communication, in particular all-reduce. This is a frequently used communication implemented in MPI libraries, and we have a well-optimized version of that, applying several algorithmic and technical tricks. The main algorithmic trick is a cyclic shift combined with a scan operation. Thank you.
Thank you. It's not yours? Okay, very good. How about this one? Yeah? Okay. Samuel, that's you? Very good. Partially mesh-free Galerkin scheme. The floor is yours.
Yes, so our work's motivated by problems in magnetic confinement fusion, where charged particles are strongly confined to move along the magnetic field lines, so you get anisotropic features like gradients and wave numbers that are orders of magnitude different looking across the field lines as opposed to along the field lines. And so our work is focused on taking a finite element method and kind of modifying it with some ideas from element-free Galerkin methods to create a more efficient way of representing these fields that use way less degrees of freedom, since you don't really need that many degrees of freedom along the field lines as opposed to across them, but we want to avoid the really difficult and sometimes impossible meshing problem of actually trying to align meshes to the really complicated magnetic geometry and physical geometry in these systems.
Thank you. You're happy with this one? Yeah. Okay. Can give you another if you like. So, Stefan, Bayesian parameter estimation of galactic binaries in LISA data.
Yeah, so LISA data, that's with gravitational waves, so that's very exotic. So if you come by, I will tell you what gravitational waves are, how we detect them, how we will detect them in the future, and how do we extract all these signals which we will detect from all the millions of galactic binaries which we will measure simultaneously, and how will we estimate these parameters. And I present you a new technique, the Gaussian process regression, with which I can accelerate this parameter estimation by a factor of 1,000. So if you're interested, come by. Thank you.
Thank you. Martin?
Yes.
Yeah. Oh. So, high order incompressible flow solver?
Yes.
Yep.
So, how do we exploit heterogeneous supercomputing clusters for large-scale computational fluid dynamics with, say, billions or even trillions of grid points? Well, essentially, we want to make big simulations on any computer. So, here I will present our solver, NECO, and our approach using modern Fortran to accommodate different computer architectures while still accommodating old legacy code. So if you're interested in porting code to new computers, large-scale CFD, or if you're like colorful posters and stickers, come by.
Thank you. Mons? How do you pronounce your name?
Mons.
Mons, okay.
Yes.
Close enough, yeah. So designing a 3D FFT library for HPC with data-centric parallel programming.
Yes, the discrete Fourier transform is essentially a matrix vector multiplication. So if you factorize this matrix into sparse structure matrices, you can speed up the performance immensely, and this is the FFT. So different factorizations are investigated in this work within the framework that is developed at ETH with DAYS in a data-centric manner. And come by if you want to talk about that.
Thank you. And Ulrich is going to tell us more about Symphony.
Yes, I'm Uli from the German National Meteorological Service, and we want to forecast with that system. That will be our upcoming system to forecast convective cells, supercells, thunderstorms, hail, and flash floods more precisely, which is a big challenge. Everybody knows that. And if you want to know which musicians play in that orchestra, which plays the symphony, which I'm the conductor of, and with which instruments, come and see me at my poster. Thanks.
Thank you. Alberto, task-based GPU-enabled distributed eigenvalue solver.
Hello, everyone. We are working on a distributed GPU-enabled eigensolver, and we are using a task-based approach using modern C++ stuff. And if you're interested in one of these topics, please come by our poster P40, right in front of Sydney Room. See you tomorrow. Thanks.
Thank you. We are at number 41. Richard, maybe you want to stand over there. Fusion of massively parallel simulation frameworks.
Yep. Hi, I'm Richard, and I'm currently working on a software coupling for a code generation framework specializing in multigrids called Exastencils, and a multiphysics framework which is more traditional, using Letzes-Boltzmann method called Warbler for applications which use both solvers. So the application domain is fluid simulations. Please come by.
Thank you. Sven, rapid update cycles.
Yes. Hello, I'm Sven Ulbrich. I'm working at the German Weather Service within the Symphony project. We want to produce more frequent and faster available short-term numerical weather forecasts. And in addition to that, we also want to improve the precipitation prediction using additional observation data and changing a microphysics scheme. If you are interested in how we do that, feel free to come tomorrow morning to my poster.
Thank you. Christian?
Hello, yeah. Hello, everybody. My name is Christian Kühnlein. I work for ECMWF. Together with our partners at CSCS and ETH, we are developing a performance-portable, finite-volume atmospheric dynamical core for numerical weather prediction. This was formerly, we had a version in Fortran, and now we are developing this entirely in Python and using the GT4Pi domain-specific library for stencil computations. So hope got you interested, and see you tomorrow at the poster session. Thanks.
Thank you. And Michele is going to talk about radio interferometry.
Hello, I'm Michele from EPFL. So with our group at EPFL, we've developed Bluebuild, which is an algorithm that is trying to solve the problem that is coming with SKA telescope. So this is going to be the largest radio telescope on Earth. And at the moment, state-of-the-art algorithms are not able to cope with the amount of data that the square kilometer array will produce. But we actually find a very relatively simple but a very efficient way of decompose the image from SKA and use machine learning method to clean the image. Come visit the poster if you want to see more.
Thank you. Oops, I think I skipped one. So that was always going to happen.
Oh, this is mine, actually.
Is it yours? Oh, okay, fine. So then let's keep going.
Cheers, yeah. Well, good evening, everyone. My name's Toby, and I've got the privilege to try to interest you in not only one poster, but four for tomorrow morning, because I'm my group's deputy here tonight. We are working, amongst other things, on fully spectral, efficiently parallelized fluid dynamics and MHD code. We've got 2 posters on methodology and 2 user posters detailing details about the parallelization and our transform. So please come by 45, 46, 49, and 51 tomorrow morning. Thank you.
Okay, thank you.
Okay, so I'm sorry that my working performance wasn't as fast as our code. That's why there isn't a poster. But I'm Dominic, and the question for my poster was how close to the peak performance can we get with code generation for our stencil-based compute kernels? And actually it turned out that we are pretty close, and we're doing quite a good performance. So if you want to know more about how we did the performance modeling and our framework, please come see me tomorrow at the poster session.
Okay. Thank you. So let me thank again all the presenters. I think they gave us an exciting overview of what we will see tomorrow from what time, Tatiana? 9 to 11. And I'm told that there will be cookies. Okay, very good. So I think we should just thank all the participants again and go for dinner. Thank you very much.